Now, when we're solving differential equations with this separation technique, we're frequently going to find that we get absolute values in the solution. And we're going to get them even with the most simple function of y. In fact, the simplest function of y is just y. And when we perform that step of dividing both sides by the function of y, we end up having to integrate 1 over y. And it's got the primitive, the natural log of the absolute value of y. So these are the absolute value brackets that show up. Then when we go to rearrange our solution in terms of y, we have to come up with some trick for removing those absolute value brackets so that we can really find the simplest version of our function. So we need to take care with constants because that will help us simplify these solutions. They're going to have powers in them because logs lead to powers. We need to also remember that if you have e to the power of something, it's always positive no matter what that constant is, and it can never equal 0. Now, we've already discussed the fact that it's not a bad idea to use a new letter each time your constant changes. I've said it's a good idea and not totally essential, because if you've gone and tidied up your solution to your differential equation by doing something like multiplying both sides of your equation by 2, then your c will become 2c, and you can say, hey, let's call that d for argument's sake. It wouldn't be wrong to keep calling it c and just acknowledge that the new c is twice as big as the old c. It's not wrong, but I think it's a good practice to use a new letter to acknowledge that you know that the constant has changed in value. But this next step, this is not so much optional, this is kind of essential. We need to define whether our constant that is an exponential term can be negative or not, or can be 0 or not too. We should write in here negative or 0 or not. Now, what do I mean by an exponential term? Well, if we've got a constant which is just, say, e to the power of something, and we're saying, hey, let's call that big A, then we need to acknowledge here that big A can't actually be 0 and it can't be negative. So you might say where A is greater than 0 if you've gone and replaced some e to the power of c with a constant A just to tidy up your formula. But if you have something like negative e to the power of c, then this is still an exponential term, and it can definitely be negative because it's got this great big negative sign sitting out the front. Now, if you want to allow your constant to be either that or that, then you could give it a new letter, call it, say, b, where b might be plus or minus e to the power of c. And in this situation, you're saying that b can actually be any real number. So where b is any real number, including 0. So then the take-home point, if you have created a constant that has to be greater than 0, then specify that. If you've then unrestricted your constant by changing it and allowing it to actually be 0 or negative, then you need to specify that you've made that change. If your constant right from the start has no restrictions, there's no need to mention any of this, of course. It's just that we're going to have a restriction and then we're going to take it away. So I think we need to change the letter of our constant, but we also need to make this really clear whether it has the restriction or in fact it doesn't. This will make more sense in an example, I think. Okay, so in this example, we need to solve a differential equation and then find 2 particular solutions. Now, we should always start by checking for those constant solutions for y. What could we sub in for y that would make y dash equal 0? Well, if y was 1, then this whole section would be 0 and we'd get y dash equal to 0. So we can say that trivially, and you can use that word or not, or you can just say note. In fact, I'd rather do that. Let's write that. Note that y equals 1 is a solution. Now, we're noting that first in case we overlook it later on, and we want to double check that the general solution we get actually includes that as one of the cases. Okay, now why are we needing to see that it's a case? Well, if we start by saying let's divide by the function of y, can you see how we're about to put 1 minus y into a denominator? And that would say, hey, y can't be equal to 1. So we need to first specify, well, y could be 1, that's a solution, and then all the other solutions will be assuming that y isn't 1. So we note this one, and then we do our usual steps, change y dash to dy dx, divide by our function of y, so we've got 1 over 1 minus y over this side, and over this side we're left with our x, we'll leave a little bit of space, and now we can integrate with respect to x on both sides, cancel our dx's, and over here now we've got an integral that's a little bit interesting. Obviously it's going to be a log, but our perfect question would have the derivative of what's on the bottom here up the top. So ideally we would like a minus 1 there, which we can put our fixed factor of -1 out the front. Sorry, just a negative, that'll do. Don't really need to write -1. So what we're going to get on this side is the negative natural log of absolute brackets 1 minus y. And on this side, we're just going to get x squared over 2 plus c. Now, to get this in terms of y, you might like to even think here, we've got a log with a base of e, we've got e to the power of some stuff is equal to this, but this sign is actually in the way. We need to get rid of that first. So we could say that we've got the log of 1 minus y is equal to negative x squared over 2 plus, now, if we've multiplied this by -1 and this by -1, technically I'd like to use a different letter there. We could keep the c and just acknowledge that it's now a negative version of itself, but let's just use a new letter. Now we can say that e to the power of all of this is equal to this part. So write that down, e to the power of x squared over 2 plus d is equal to the absolute value of 1 minus y. And we don't want to forget our absolute value brackets here. Now, tidying up this side is where it gets a little bit confusing, but after you've done a bunch of these, you'll get the hang of it. We need to acknowledge that if we've got e to the power of something, let's just say e to the power of m plus n for argument's sake, that's e to the power of m times e to the power of n. We know this index law, right? And that's the one that we want to use, because we could tidy that up and say, hey, let's just make an expression for that whole second part. So what we've effectively got here is e to the power of our x part multiplied by e to the power of d. And I'm going to call e to the power of d a. At the same time, I'm going to write all of this on this side. So I'm starting to get my y's on the left. Not that it really matters, but I just think it's tidier that way. So I'm going to use a new constant here, a e to the minus x squared on 2. And that whole expression there is now equal to this. Now, can you see that a is actually just e to the power of d? So e to the power of d has to be positive. Can't be 0, can't be negative. So I'm going to specify here that a is greater than 0. How do I know? Because a is equal to e to the d. And you could write that down if you like. A is equal to e to the d. That last bit's not essential, but this bit is. Okay, so now if I want to drop my absolute value brackets and say, all right, well, what's this thing when it's not that? Perhaps it could be the plus or the minus version of this a. Well, I'm going to want to use a new letter now. If a could actually be the negative version of itself, let's call it now b. And now all I've done is change a to b. But what I've done, importantly, is I've acknowledged that if everything on this side inside these brackets could have been positive or it could have been negative, we made it positive here so that both sides were positive, then if it now could be either, then clearly b can be anything. So we need to state over here, so where b is any real number, including 0. Okay, so we're close, but we need to get the y by itself. So if we add y to both sides, it would get it over this side, but we need to subtract that whole thing from both sides. So now I can just tidy up by saying y is equal to 1 minus b e to the minus x squared on 2. And that is now my general solution. I've got one specific solution I've found already, and then this is my general version. So now let's continue over this side. Let's find our specific solutions that we've been asked for. The first one, when x equals 0, y equals 0, and subbing that in, we can say that 0 is equal to 1 minus b e to the 0. Well, e to the 0 is just 1, so 0 is equal to 1 minus b, and b must be 1. So then our specific solution is y is equal to 1 minus, and subbing a 1 in there, we just get e to the minus x squared on 2. That's our first specific solution. And then for the second one, subbing in when x equals 1 and y equals 1, we have 1 is equal to 1 minus b e to the minus half. Now this one is a little bit trickier, but if we subtract 1 from both sides, then we're saying that 0 is equal to negative b e to the minus half. Now e to the minus half is a number, so that means it can't actually be 0, which means that if two things are multiplied together to make 0, then negative b must be 0, which means that b must be 0. So if b is 0, then this whole section is 0, and we end up then with the solution y equals 1, which we actually considered way back at the start. So if we hadn't considered it, okay, the question was going to prompt us to find it anyway. But as we saw in the previous example, sometimes we'll get a little bit confused when finding an extra solution. And if we're not prompted, we don't want to miss out on finding that really simple solution. So finding at the start still makes some sense, and knowing that it's there when you're working through and knowing that it might crop up also makes sense. Now for an example like this, it's worth noting that there's always more than one way to do it. So let's get rid of part B here and actually just go back to part A and see how it could have looked a little bit different. If we had decided that over here it would be nicer not to have negatives, we could have fiddled around with things a little bit. Now this requires us to understand that if you want to change an expression that looks like this into one that looks like that, all you've got to do is multiply it by -1. So here, if we don't want 1 minus y, and we're over there thinking, oh gee, when I divide that, I'm going to have 1 minus y, it's not going to be a perfect question. If we wanted to, we could have actually said, let's change this into negative bracket y minus 1, switching these terms around. And if we'd done that, then we would have changed our y dash to y dx as usual. We would have instead divided by y minus 1, considering that now we're leaving negative x on this side. So when we integrate both sides with respect to x, what we'd end up with then is here we would have had the natural log straight away of y minus 1. We wouldn't have had that awkward negative out the front. But over here we would have had the negative, and we would have had negative x squared on 2 plus c. Now this one looks a little bit different from this one. It's important to note that this c and this c would be different. And if we kept on going with this sort of working and tidied it up, what we would have got the exact same thing, except that our terms would have been around the other way here. So on the next step, we would have said, all right, e to the power of minus x squared on 2 plus c is equal to the absolute value of y minus 1. And then we could have adjusted this and said, all right, let's let e to the power of c be some constant. We'll call it a. So we've got a e to the minus x squared on 2 is equal to still an absolute value, and we would have said that a has got to be greater than 0. And now to drop those absolute value brackets, we can write this over this side this time and that over that side, and just say we've got y minus 1. We would have had to change a into, let's say, b, and specify that b can be anything. So b is any real number. We would write that out. And now to finish up, we would have added 1 to both sides. So our formula would have looked a little bit different. 1 plus b, e to the something or other. Over here we had 1 minus b. Now, does that matter? If someone beside you's done this working and you've done this working, are you going to get the same particular solutions? Absolutely you are. The only difference here is that you're subtracting b and they're adding b. Well, we haven't found what b is yet anyway. And your working for the second part might look a little bit different, but your solution will be exactly the same. Now, I've said this before, don't get caught up too much on trying to make your life easy with the way you separate your differential equation. But do acknowledge that there's always more than one way to do it. And if you're looking at worked solutions, say, and you're confused because it's different from your working, it might be that yours is perfectly good. It's just somebody's gone the other way. And so their working is going to look different, and their constant might also be different. Another example now so that we can really get the hang of this technique. We need to solve this differential equation and find 2 particular solutions. So the first thing to note is our constant solution, which is that if y is equal to 0, then y dash will equal 0. So that is a solution. Now let's follow our usual process, change y dash to dy dx. Let's divide both sides by the function of y, and that leaves the x on this side. Then let's integrate both sides with respect to x, and we get this situation. Now, integrating this side, I can see that we've got the natural log of the absolute value of y is equal to x squared over 2 plus c. So e to the power of all of this, x squared on 2 plus c, is equal to the absolute value of y. Now, we can tidy up an expression as soon as we see something added or subtracted in the powers. We use our index laws to split it up and say, let's come up with an expression for e to the power of c. Let's call it a. So a e to the x squared on 2 is equal to the absolute value of y. Now we need to specify here that a is greater than 0. And why is it greater than 0? It's because a is equal to e to the power of c. And you can write that down if you want to. This part is optional, this part is essential. Now on the next line, we want to drop those absolute value brackets that are around y. So we need to acknowledge that y could be negative here. Now, if it could be negative, we need to allow this side to be negative as well. And we can do that by changing our constant to b. And we've still got the same exponential part and saying that b is any real number. Now, you can do that with fancy notation, or you can literally just write it down. Okay, so that's our general solution. Now we need to find particular solutions. So we need to let x equal 2 and y equal 3 and find out what the value of our b is there. So subbing in, we get 3 is equal to b e to the 4 over 2, that's 2. So b is going to be 3 over e squared. So now we need to sub in that value of b to our general formula here. Now, if you just go straight ahead and blindly sub it in and write it down like this, it's not wrong, but it's certainly going to look a little bit clunky, and I think that we can do better. So looking at it like that, I can see that the b could be written as 3e to the minus 2. Now, if I'd just written that first up, which would have been quite easy to do, going from there to there, then I would have this. Also looks pretty clunky, not wrong, but perhaps writing that down helps us, let's just not have things run together here, take our next step and say, let's tidy up. And if we've got bases that are the same, then we can add the powers. So we've got negative 2 plus x squared over 2, and that can be written best as x squared over 2 minus 2. And I think that's the neater version. So that's our first particular solution for here. So that's for part 1. For part 2, I'm sort of running out of space here. I need a bigger whiteboard, but you've got plenty of room on your page. Let's let x equal 3 and y equal 0. So subbing that in, we've got 0 is equal to b e to the 9 over 2. Now, if two things are multiplied together to make 0, one of them has to be 0, and this part can't be, so this part must be. So therefore, b is equal to 0. So then rewriting and subbing in, we actually just have the line y equals 0, which is the sort of slightly trivial solution that we spotted first up right in the beginning, and we've been led to it through a different method.